So let's imagine we have a proton. It is released at point A, close to a positively charged fixed particle of 9 microcoulombs. The question is, how fast is the proton moving when it reaches point B? So in this question, we have a proton, which we know is a positively charged particle. So let's just make a note of that Q1, we'll call the proton Q1, and we'll call the fixed particle Q2. Q1 is a proton. And remember, if it's a proton, it has a charge of E, that 1.6 times 10 to the negative 19 coulombs. And Q2 is our 9 microcoulombs. So let's make a note of that, and let's change that micro times 10 to the negative 6 coulombs. So there's our two charged particles. And what we want to find in the end is the final velocity of this proton. Okay, so what we have to note here is once we have the two particles, as that particle moves from point A to point B, its change in energy is going to equal 0. That tells us that the change in the kinetic energy is going to equal the negative change in the potential energy. Well, kinetic energy is EK final minus EK initial, but this is actually going to be the change in electric potential energy. So we can find that change in electric potential energy in a second here, but now if the proton is starting from rest, the initial kinetic energy disappears, and we have 1/2 m, and that mass is the proton, v final squared, the equation for kinetic energy, and it's going to equal the change in electric potential energy, of course, that negative. So a little bit of algebra here, and we can solve for v final, and v final then is going to be the square root of negative 2 delta EP all over m of the proton. So if we can find the change in electric potential energy, we can plug that value in there, and we can find that final velocity. So delta EP is going to be the electric potential final minus the electric potential initial. We have two radial distances, and if we plug in our equations for EP final and EP initial, the final and the initial just become the radial distances. If we notice that it is originally 0.25 meters away and it ends up at 0.75 meters away, just do some factoring, take out the KQ1, Q2, and plug in all the numbers. And in the end, we get a value for EP. Now it's going to come out negative, and we get negative 3.45. And can you imagine this? 6 times 10 to the negative 14 joules. Well, now that we have delta EP, we can take that value, we can go back up to our final velocity equation and plug in our numbers. Notice what's nice here is that there's a negative from the change in electric potential energy and a negative under the square root. Those negatives cancel each other out. Plug in the value using the mass of the proton, and in the end we get a proton moving at 6.4 times 10 to the 6 meters per second. An incredibly high velocity. That proton just moving 50 centimeters because of that electric potential energy.